Hello friends, in this video I'm gonna show you how I made the seat suspension for my Volvo V90. I love the car, but the suspension is very hard. Replacing the entire suspension could be very expensive, so I said, why don't I just soften the seat? The system pivots the entire seat around the front wire rope springs, featuring a 100mm swing. I designed the bottom of the car in CAD, and I made a stainless steel cradle that will connect to the rails of the seat. The seat adjustments are still available, but there are some limitations. I bought a spare Volvo seat in order to experiment outside the car. I also made a vibration generator in order to evaluate the results. A soft suspension needs a lot of range, but I don't have a lot of space behind the seat. I decided to split the motion on two vectors, linear slides on the bottom of the car and shock absorbers on diagonal. For dampening, I used some wire rope, and that reduced the bounce back quite a bit. To keep the driver in the sweet spot, I decided to use a linear actuator that moves the seat in relation to the shock absorbers. I chose the Thomson DT1205A5-12. It runs at 12 volts and it puts out a maximum of 250 pounds of force, however, is not very fast. It also has a built-in potentiometer for monitoring the position and a clutch. This actuator also compensates for the seat motion while accelerating and decelerating. It also prevents the suspension from resonating when the terrain has repetitious ups and downs. To monitor the vibration, I installed two inertial measurement units, namely the MPU 6050. One of them monitors the car chassis and the other one the back of the seat. They both share the same IC² bus, making the wiring simpler. For visualization, I'm using the new Arduino Giga and the Giga display. The unit is very fast, featuring two processors. In my case, I put the M4 processor in charge of data collection, namely the Z-axis acceleration times 2. It also collects the height of the seat and the position of the linear actuator using two analog reads from two potentiometers. The M7 processor runs the display and the motion of the linear actuator. It gets the updates from the M4 every 10 milliseconds, and it feeds the data in a closed-loop PID algorithm. The actuator motor control is done by pulse width modulation fed in a Toshiba BTS 7960 H-bridge controller. On the screen, we see the vibration monitoring for the car chassis compared to the seat. While the amplitude is comparable, the seat shows curves that are a bit softer. I guess that's what the suspension is supposed to do. It won't eliminate vibration, but it will make it smoother. The blue dots represent the motion of the seat in relation to the car as fed from the linear pot. The green dots represent the motion of the actuator trying to compensate for the large swings. I'm generally happy with the results, however, this is a pretty slow reaction system. Mechanical actuators are known for having a lot of inertia and delays. I'm working already on the second generation featuring a linear electromagnetic motor. The idea is to compensate for each bump in the road in a fast, proactive manner, kind of like a camera stabilizer. The project was a lot of fun, and having my engineering under my butt every day brings me a lot of satisfaction. Stay tuned for part 2.